Gone. So it doesn't necessarily focus on me. There we go. All right. Except it's being pulled. Which way is it moving?
To the right.
All right, so the velocity is in that direction. It's being pulled. So I have some tension here. And what else is given in the problem?
The friction to the left between the sled and the ground is equal in magnitude to the 42 Newton tension in the rope pulling the sled to the right.
All right, so this is 42 newtons. And I said that the friction between the ground and the sled, well, let's just go do a force diagram here. So I've got the boy here, I've got the sled, and then I've got the ground. And I know that there's a tension here, and there's a friction here. That's 42 newtons. It's 42 newtons. Put up our checklist, F down. All right. First off, that tension right there, that's an example of other. Because I told you there's a tension there. I don't think I mentioned what was pulling, just that there was a tension there.
That says by a rope to the right on the ground.
Yeah. So I guess I could, if I wanted to, put a rope over here with a tension going back that way, but I still don't know what's pulling the rope, and it doesn't matter to the problem. And so that's an example of other, where I'm going to have this tension here, but I'm not going to draw its pair, just because I don't need it. But I do know there's just something over here with a 42 newtons acting backwards, but irrelevant to the problem. All right, so forces come in pairs. Where's the other part of this friction pair? Going. All right. What are the other forces involved? Going. I heard weight.
Onto the ground from the sled.
Still working on prepositions here. All right. So it's going. So which way am I drawing the arrow on what object?
Down from the sled.
I draw it on the sled.
On the sled.
Okay. So down on the sled. What's the other part of that pair?
From the ground.
On the ground. I'm drawing the arrow on the ground, not from the ground. This is the arrow from the ground. This is the arrow on the ground. I think you would draw it correctly, just I put a little subscript there, but probably need it. All right.
Then from the boy pointing towards the ground, and then from the ground pointing towards the boy. No?
The boy to the ground.
At some point, I'm just going to let it go, but not quite yet. Same issue as Hannah was having. I'm asking where do I draw the arrow, and I'm drawing the arrow on something.
Drawing the arrow on the boy going down.
Yep, there we go. That's the language. And the other one?
On the ground.
All right. Weight is done. I have only two small objects, not counting the planet. I have only two small objects, so I've got my two pairs there.
Normal force from the boy onto the sled. Going up. Normal force.
Drawing up on the boy.
On the boy.
And the other part of that pair?
And going down on the sled.
Okay.
The same for the sled.
I assume you mean that up on the sled and down on the ground?
Don't you assume?
All right.
That's
Say it
what
again
she
then?
meant. Like, sorry.
That's what I meant.
That's what you meant? Okay. Y sub, I guess, S. Let's see, those are in contact, so I should have a pair there and a pair there. So my normal force is done. Tension, was given in the problem, so that's done. And it was the other, so. Friction. We got one friction pair there, is that it?
No.
Where else is there friction?
Between the boy and sled.
Which way is it acting on the boy?
To the right.
It's one of those two, or actually potentially neither. Let's come back to this later. All right, so the first question was, what is the force?
The magnitude of the gravitational force acting on the boy.
In other words, what's the weight of the boy without worrying about direction? So we're asking for this. And what's the formula?
Mass times acceleration.
More specifically, when finding weight, what kind of acceleration?
Due to gravity.
Yes. So when you're finding weight, the formula W equals mg, it basically goes back to F equals ma, which I think was referenced last time. So this is the acceleration due to gravity. It is not a constant. It is not gravity itself. Gravity is a very huge topic, of which this is one small aspect of it. What is the approximate value of the acceleration due to gravity near the surface of the Earth? I'm going to leave off the 1 for now, and I'll explain why in just a moment. 9.8, don't forget units.
Squared.
Yep, squared. What about in US customary units? What is it with feet in seconds? You sometimes see this in math class, although judging from past students, they don't really explain where the number comes from. But it's approximately 32 feet per second squared. All right, so the 9.81 that somebody mentioned, if you want to use that for generic value, that's fine. Hewitt often just rounds it off to 10. The reason why I don't put the 9.81 is I've had too many students always use 9.81 for the acceleration due to gravity, no matter what. And in Winston-Salem, it's closer to 9.798 meters per second squared. At this point, they've done a more sophisticated survey of it, but they used to actually have a device. Let's make sure I'm oriented right. Let's see, we're in Tech. Silas Creek is over there. So, what was it over there? It's the road just past Miller Street coming this way. There's a road that shoots off away from the school. If you follow that to the median, there used to be a device right there which was measuring the acceleration due to gravity. So we actually have, probably better than most places in the world, pretty accurate value for the acceleration due to gravity here. All right. So you would take the mass of the boy, which I assume I gave.
Do I put a check on my name?
Sure. Okay. Kimberly? No. No. Kimberly. So one clue that this is the mass, I think I said in the problem his mass is, or did I just say a 35 kilogram boy?
A 35.
Yeah. So the big clue that this is the mass is the fact that I'm using kilograms here. Kilogram is a unit of mass. It is not a unit of weight, despite how it might be used elsewhere. In physics, this is a unit of mass. All right, so you got a formula, plug and chug, use your calculator, don't mistype, and you get 340 something or 350 if you use 10 per G, meters per second squared. All right, what was question part B was, what is the magnitude of the gravitational force on the sled from the ground?
Yeah.
So I'm asking to find that. Similar process. I give you the mass, and again, units of kilograms. I think it was 6 kilograms? Okay. Times 9.8. And then I think part C was the normal force on the buoy.
So for, so for 13 number 8, it's 35 times 9.8?
Yes. If you put down 35 kilograms, that's one of those cases that I was trying to get across before when I just completely blew it last time, and I would go, no! Again, please don't put, if it's asking for a weight or a force, kilograms is not in the final answer. All right, so the next one was the normal force acting on the buoy from the sled or on the sled from the buoy, one of those two.
The sled from the boy.
On the sled from the buoy. So I'm asking for this right here, which would be the same as that one right there. Brittany, you had a question?
Yeah, I'm sorry, you may have just said that, but I was looking at, said the answer to this, but I had, weight equals, mass times the gravitational
Acceleration.
acceleration. So, all of my answers, that would be in newtons, right?
Correct.
Okay,
When you do kilograms times meters per second squared, you get newtons.
okay, gotcha.
And why? Why is a kilogram times a meter per second squared equal to a newton?
So you can't convert it to a pound?
Well, you could.
Well,
That would be an extra step. It's a very simple answer of why kilogram times a meter per second squared is equal to a newton. Okay.
Newton is a measurement of
Say it with confidence, whether you're right or not.
It's not right.
Newton is a unit of force. I think that's what you were going for? Okay, with confidence. But the reason why a newton is a meter times a kilogram, oh, sorry, try that one again. A kilogram times a meter per second squared, because it's defined that way. The powers that be said, we're going to do that. There's no underlying message, there's no underlying reason there other than they wanted to honor Sir Isaac Newton. He dealt with forces, and so they decided to name a unit after him, and they just defined it that way. So you see these three lines here. It's more than just equal. It is equal by definition. If you've had slightly more sophisticated math class, that was the symbol that I saw used, the equal sign with the triangle over it. In physics, we always use the three lines. All right. So it would be in newtons, I think, which is ultimately the question, the answer to your question. Other questions up to here? All right. So, which way is the sled moving?
You're right.
Okay. Is it moving up or down?
Even, it's constant.
I heard a neither over there. All right. So there is no movement up or down at all. More specifically, there's no acceleration up or down at all. The vertical velocity, the vertical component of the velocity is 0 and stays 0. Therefore, what do we know about those two forces
They're equal.
in magnitude? We know his weight, therefore we know the normal force keeping him up,
Is it same?
and therefore we know the normal force he's pushing down on the sled.
So would you just subtract them?
Subtract what way?
So, the boy's weight from the weight of the sled?
No, it just, all we're worrying about is, he's in equilibrium, he's vertically in equilibrium, therefore these have to cancel each other out. This was, whatever that number was. We'll just say 350 newtons for right now. That's 350 newtons, therefore that has to be 350 newtons. And the force the sled pushes up on him has to be equal to the force that he pushes down on the sled, equal in magnitude. So no additional subtraction or anything like that.
So essentially it'd be the same as the answer to A.
Yes. All right, now, I think the next one was the normal force exerted on the sled from the, oh, yes, Brianna.
I'm sorry. So weight and force and magnitude is equal? Or,
Wait, say it again?
so weight and force and magnitude is equal?
I have two forces acting on him, his weight and this normal force. If he's in equilibrium vertically, in other words, he's not accelerating up or down, his vertical velocity does not change, then those have to cancel each other out. Does that answer it?
Yeah.
Okay. So the next one is asking for, what's this wording?
The magnitude of normal force acting on the sled from the ground.
On the sled from the ground, so I'm asking for this right here. Unlike with the boy, I had two forces acting on it. Now with the sled, I've got three forces. What is the total force acting vertically on the sled?
The force from the boy and from the ground?
Total force. I got three forces.
Would you add the boy and sled together?
I would add all three forces together. What was the total vertical force acting on the boy?
343.
Ooh, no.
Wait, zero?
Ooh.
I don't know.
Total force. When I say total, I'm talking about a sum. We're adding it together. Apparently the first bit is slowly seeping in. Pardon? I heard a question over here.
Would it be 35?
No.
Would it be 400?
No. Not quite sure. There are a couple of different questions sort of thrown out in the air there. So no to the question that I think I'm asking. All right. The weight of the boy was around 350 newtons-ish. Any questions about where that comes from? Or for the grammar purist? Anyone have questions from where that comes? Why was this equal to the same thing? Same magnitude? How do you know it's an equilibrium?
The force not following through.
All right, too many voices at once, sorry. Tana?
They cancel each other out.
They came what?
They cancel?
Why do we know they cancel? Yes, they do. Why do we know that?
Because he doesn't move up or down.
Okay, at all. All right, so he's not moving up or down at all, its movement is that way. What about the sled? Is the sled moving up or down?
No.
Therefore, what do we know about the sum of the forces? Okay, and so if they're in equilibrium, what does that mean in terms of the total force?
Zero.
Yes. I have two forces down, I know that value, and I know that value because we've already calculated those. That's the answer to part B, and that was the answer to part C, I think. This force right here has to cancel out the sum of those two. I got two down, I got one up, they gotta balance each other out. So that's gotta be the sum of those two.
I think I'm right, I don't know. 401.8.
It seems like it should be somewhere around there because the weight of the So this was somewhere around 350, that's somewhere around 60. So 410, something a little bit less than 410. And you said 401 point something?
Yeah, I just added the weights of both the boy and the
Yeah.
sled.
That's what I was about to ask you, are we, because I really wanted to ask, were we adding the weight of the boy acting down and the weight of the sled acting down?
Yep, it would be just some of those two. Ultimately, now, from a practical point of view, yes, you're absolutely right. Technically, what you're adding here is the weight of the sled and the normal force the boy exerts on the sled, which in this case is equal to his weight. If the boy were jumping up and down on the sled, then those are no longer the same. Yes, Hannah.
Why do we add them? I'm just a little lost.
All right, I got 3 forces acting on the box. Or if you prefer me to draw it as a pull, I've got 1 pulling up and 2 going down. If this is 10 newtons, and that's 30 newtons, and this is in equilibrium, what does that have to be in order to balance that out? You just added them.
I get it now.
Okay. All right, other questions on part D? And there's 2 more parts. Sorry. All right, so the magnitude of the total force acting on the sled. I think we just answered that, but what is the magnitude of the total force acting on the sled?
401.
Total. We got 3 forces acting on the sled.
Is it 401?
Actually, we have 5 forces acting on the sled. Sorry about that. We got 2 down, 1 up, 1 to the right, 1 to the left. Or from your point of view, 1 to the right, 1 to the left.
0.
Yes. How do we know it's 0?
Because it's an equilibrium.
Yes. Once you've established equilibrium, there are 3 things, try that one again, 3 things that are true if in equilibrium.